Okay. Whoa! All right. Okay. So, shh. Nobody came, so it's already quiet. So, Friday, sunny, nobody comes. Cloudy, nobody comes. I don't know. It's always an excuse, right? So, Friday, yeah. Okay. Lecture in a minute. We're going to talk about these things that are formulas. And formulas have Boolean variables, okay, with ands and ors and negations and that sort of thing. But we're going to talk about a certain kind of formula called a Horn clause. And there, what you have is clauses that are composed of implications, where on the one side you have, you have only positive literals. Okay, you have no negations in these clauses. And you also have some negative clauses with ors. So not X or not B. Okay, so we're having a general formula where you have all these clauses, and now you need to set the variables so that all these clauses are true, right? So all the clauses are true. Okay, so now basically what we're gonna show you is a greedy algorithm that. That you only set variables to true if you have to. Now, an implication, A implies B. If you set A to false, is the implication true? P, let's use the CS70 notation. P implies Q. Okay, that was a joke. Okay, so and if P is false, is P implies Q? Is that whole clause? Is it true? Okay, that's right. So setting things to false for implications is a very safe thing. Okay, you're not implying anything if you set the left-hand side to false, right? If cows could fly, I would give you $1 million. That's pretty safe because maybe it's not so safe. We could talk about definition, but in sort of, I'm saying it's false. Cows can't fly. So. I'm safe from giving you $1 million, right? Okay, so I don't want to set things to be true because every time I set things to be true, an implication means I better start making the other one true. So setting things to false is a good thing. So that's what we're going to show here with these kinds of implications. You might as well just not try to be conservative. Okay? And set cover, there's this other problem where you have a set of elements and you're trying to cover it. Okay? So there's like good examples where you're trying to put stores that are within 100 miles of everybody. So the set that a store covers is all the people within 100 miles, and you want to cover everybody in your state, right? This is Starbucks. You want to over-cover every corner, right? This is the set cover problem, and you want to find a minimum number of sets that cover all the elements. And we're going to say, again, this is a greedy thing. We're going to say choose the largest set that contains an element. And we're going to prove that this works. It gives an order log n approximate solution. This one we're not going to find the optimal, but we're going to find a solution that within a log n, that is within a log n factor of optimal. And the idea is if there is an optimal of size k, you cover at least 1 over k of the remaining elements. And from this idea, we can actually construct the approximation. Okay, and then we're going to do this crazy path compression thing. And we'll do that. Okay, so let's think about this thing called a taint analysis. You're reading from the web. Okay, I have a program. It's reading from the web, right? It's a web server or something or whatever. It's maybe a database-packed web server, right? So you read a response. That's dangerous. When you read text from the web, that's dangerous. If you use that text and if you somehow they can make you execute a part of that text, you're in trouble. So you have to be very careful how you deal with this text, right? So now if I go and I add it to C, so we know now that we read this thing from the web, so A is dangerous. And now we added something to A and made it B, so now we think, well, B is dangerous, right? We better watch out where we put B, okay? And so on. Right? If you then put B into some SQL command, Maybe B, maybe plus here is concatenation, right? It's polymorphic. Who knows what polymorphic means? Yeah, plus can be more than one. If it's strings, it'll do concatenation, right? You see that in Python. If you plus 2 strings, they concatenate. But plus 2 integers is adding. So that's the polymorphic plus. Plus is the polymorphic procedure. It depends on what the arguments are. Anyway, that was an aside. SQL command. Now that command may be delete everything in your database, right? Which is problematic. Okay? So this is a very good skill if you work for Putin. So A is input from the web. A is tainted. And we can actually see this whole reasoning here. We see that. We see that A is read. We can actually write down the thing. A is tainted. If A is tainted, then B is tainted. We just look at the text, and the text tells us that. Okay? If B should not be tainted, that's the last clause. So I have 3 clauses here. Okay? And one says the logic representation is there's variables. A is tainted, B is tainted, and B should not be tainted. Right? A is tainted, B is tainted. So A is tainted, we have this clause from the first line. Okay, that's what that clause is. We have an implication that says A is true. There's nothing here, so A has to be true. Now, A implies B, that's the second thing. A is tainted, B is tainted. And finally, not B. You don't want B to be tainted because you see that B is used in an SQL command. Okay? So you write down these clauses. So it's a program analysis sort of task. So this is now this is a set of clauses where I have implications, where these are only positive variables, right? There's no negations here. And this is I have some clauses. I have this clause that says I don't want B to be true. Right? That's what that says. Okay? So that's an application. So is this satisfiable? Well, not in this case, because A is true. If A is true, B has to be true, but we don't want B to be true. So this is bad code. Right? Okay. So you would spit that, your compiler would do this analysis, this taint analysis, and then it would say this program is tainted. Don't use it. Okay? Okay, so implications are ands of positive literals imply one positive literal. That's what we just saw. X and Y implies Z. Negative clauses is the or of negative literals. You, not you, or not V. Okay. Now the taint example is just this, right? These satisfy these things. The implication for A is of the first form. A implies B. Of the first form, and the last one is of the second form. True is a problem. Here, true is a problem. Because implications are fine. They're always going to work as long as you just set everything to true. That kind of works. But the problem is when you set things to true, these negated clauses may be not true is false, right? Not true is false. Okay? So you want to set nothing to be true. If every literal is false, all the implication statements are good. Okay? Because if every literal is false, and all the or statements are true, except for this one. This implication statement is a weird implication statement. It just says A is true no matter what. Okay? So this is really just saying A has to be true. So except for statements that look like this, which say A is true, which is you can represent with an implication where there's nothing on this side, you're good. So it's sort of clear what the algorithm wants, right? The algorithm, what you want to say is like, let's not even worry about the negated clauses, okay? Because really, all these negation clauses, they're only problems if these things are true, if any variable is true. Otherwise, they're fine. Any variable that's false, the not of it is true, and you're happy. Okay? So what we're going to do is we're going to throw out all the negative clauses. We don't care for now. What we're going to do instead is we're going to think of this problem as we have just the implications, and we're going to try to assign as few variables to true as possible. Or even said differently, we're only going to set a variable to true if we have to. Okay? That's what we're going to do. We're never. Is there a variable that has to be true in this one? Is there a variable that has to be true? We're only going to set literals to true if you have to, right? And now if you know if at the end you've only set true variables to true if you have to, then you can just check your negative clauses. Right? Anything that's false is fine for the negative clauses. And the ones that are true had to be true. So therefore, if you had a not B and if you have a not x1 in your negative clause, you're done right there. It's not satisfiable. So you don't really have to think too much about the negative clauses. As long as you can only set literals to true if you have to. Okay. So now x1 must be true, right? So now we say x1 is true. I'm calling it red because it's a bit dangerous, right? Do you see something else that must be true? Yeah, I made it colorful for you. So x3 must be true, right? So x3 is true. Do you see something else that must be true? Yeah. So what's the next one? Matthew? Is it Matthew? I outed you. I'm sorry. That's Matthew class. Class Matthew. This is the class. Okay. So x must be true. Okay. x4 must be true. Okay. So that's the solution. Does anything else have to be true? Right? Does anything else have to be true? No. Right? These two implications that are left won't fire off because x5 is false. So x5 and x1 being true is false and true is false. So there's no implication there. Right? I don't need to set x5 to be true. So these are true. We could also set x5 to be true. We could set everything to be true. We don't really care, right? With these implications, we could have just set all of them to be true and they would be fine. What we're trying to do is deal with the negative clauses by not looking at them, right? But we're just going to set things to be true if we have to. Okay? Okay, so that's it. Same as Hornstadt, right? So Hornstadt had negative clauses, no negative clauses for the above algorithm. But if you set a variable, if you have to. So any variable set to true must be true in any satisfying assignment. And it's by induction, right? At the beginning, the only things we set to true were the individual variables that only had implication on the right side. Okay, so they had to be true, right? They had they had to be true. And now once we do that, by induction, the first k that were set to be true had to be true. We knew that. Okay, and if that's true, and then the k plus first variable has to be true because all the ones on the left-hand side that fired off, they were true, so that one had to be true. It's a triviality, right? So it must be true. Now, Horn has negative clauses. Negative clauses are only problems for the true variables. I already told you this proof. I'm just repeating with the slide. And just so you know, I didn't read from the slide. The slide's read from me. Okay, so wrote it down. Okay, so any variable that is true must be true. Okay, so the material is hard in this class, but understanding my jokes is even harder. So, the level of complexity is shocking. So any variable that is true must be true. Okay, so if a negative clause is false, it must be false. Okay? Because the negative clause, if the variables are false, they're negated, so they're true. Okay? Okay, so any SAT formula... This is a problem, right? Here, why can't we run this algorithm for any set of implications? So x1 being true doesn't tell you whether x3 or x2 is true. Now you have a choice. Okay? So this is why the algorithm doesn't work in general. Okay? You don't have to set x3 to be true. You could set x3 to, if x1 is true, one of x2 or x3 is true. But once you have two choices, it gets way more complicated because these 2 times 2 will happen. Yeah.
What does SAT stand for?
Oh, sorry, SAT. Satisfiability. Okay, a SAT formula is just any formula which is a bunch of clauses with on the same set of variables, and you want to satisfy all the clauses. Okay. Sat is satisfiability. Yeah. Yeah. It's not. It's also the first 3 letters of my name, but that's not relevant. Okay. So there's no polynomial time, and we're going to talk about this. We're going to talk about the fact that this is actually really a hard problem. Horn is a very special set of clauses where we can do this. Okay? And this is something we'll talk about later. We don't have a lot of time today because I need to do path compression. So set cover. So the inputs are items. You have a set of items, and you just can number them. You can name them arbitrarily, 1 through n. You have a set of sets, which are a subset of this set of items. Okay, each one is a subset of the set of items. And you want to find the fewest sets that cover B so that the union is B. That's what I mean. Okay, city blocks. I may want to cover all the blocks in the city using cell phone tower locations. Right? I want to be able to make sure I get to every block. So some location has a set of blocks it can cover. Okay, and so on. Right? You could have customers, and you want to have Walmart locations that cover a subset of the customers, right? You can say this Walmart needs to be within. I want to cover all the people in Texas, and everybody has to be within an hour, right? So job responsibilities, right? People with job capabilities. Maybe there's people who can do this subset of jobs. You want to cover all the bases. Okay, so this is just really very useful, right? I can go on and on of set cover applications. Okay, and this is pretty cool, right? Touch factory needs, touch seeds. Some factories can make different things, or factories need different things, and suppliers have different subsets of things that they can give you, and they give you a good price on, right? Okay, and this is literally a real problem. I think there's not thousands of suppliers for GM. I think there's tens of thousands, right? Okay, so now you want to choose a set S of I that has. So now the greedy algorithm here is fairly clear. You have this set of items. The greedy algorithm is, well, you choose the largest set. You choose the set that covers most of the items. You're trying to cover the items, right? So choose the one that contains the most. Okay, so then you remove the elements in S from all the sets. You say, these city blocks I covered, I don't care about covering anymore. Now let me pick a cell tower that covers as many blocks as possible that are left. Right? Okay. Rinse and repeat. Okay, number of sets is number of iterations. So how many iterations? Right? Here, the analysis of this argument is how many sets do we use? It's the number of iterations. Right? Each iteration we pick one set. Okay? Is there questions? I'm going a little fast. Okay. Okay, how many iterations? Set cover, let's assume, we always, like when we do this greedy, we kind of say, let's think of an optimal one out there. So we're going to do that here too. Let's assume there's an optimal. It has a size, so we'll just call that size K. Okay? Is this clear? That's just a set cover of size K, and say that's the smallest K, but it doesn't matter. Just say there exists a cover of size K. Again, a set cover of size K is K sets that cover all your items. Right? K sets that cover all your items. I'll say it a third time. K sets that cover all your items. Okay? So a set, there must be one of these sets that covers at least 1 over K of the remaining items. However many items you have left, K sets cover them. Right? So one of them must have size at least 1 over K of the number of remaining items. Right? Does that make sense? Just a simple division. You just say to yourself, well, there's K sets that cover all the remaining items. However many remaining items, there must be one set whose size is at least N over K. R over K, where R is the number of remaining items. Okay? Okay, so now, when you do that, you made progress, right? Now you have fewer items you need to cover. Okay, so you have a notion of some amount of progress. So at time t, you used to have some number of items left. After you cover 1 over K of the remaining elements, how many do you have left? Well, N over T, N sub T minus N sub T over K. right? There's some set that covers at least 1 over k of the items, nt over k of the items. So now once you use that set, you must have reduced the number of elements by nt over k. Okay? So in iteration k, you cover 1 over k times nt of the remaining items. So nt plus 1 is less than, you might have covered more, right? You might have covered more of these items. So that's why there's a less than or equal to. So you know you cover at least this many items, so you throw them out. So the number of items you still have to cover is nt minus this many. And there's this crazy thing you can do. You can factor out the nt. Oh, that's crazy. Okay, so then you can also do something called induction. And you can see that, well, you can say every time you're multiplying by 1 minus 1 over k. So after t iterations, you know your size is less than 1 minus 1 over k to the t times n0. Right? Okay? It's factoring in induction. When do we stop? Well, when we don't have any items left. Right? Yeah. Yeah, tell me. It may have less than 1 over k of the original size. But the optimal set cover, okay, so this is a subtlety. He's saying at the beginning, you're sure that one of your sets has n over k, where n is the total number of items. That's what he's saying. And he believes that. Okay? But he's saying, well, in the middle, is that really true anymore? Because now it's all changed. N is changed and blah, blah, blah. Okay, so let's think about it. Now, say you have nt left. Now, the original set cover still covers these items. Right? So, even though you remove some of the items from those original sets may not be n over k anymore of size, but they're at least nt over k. Because the original set of k sets covers all the items, including the ones that are left. Does that make sense? K. It's strictly greater than nt over k. There's k sets, the k original sets covers all the nt items. Okay? So one of the sets must contain at least nt over k of these items. Okay. No, there's no k minus 1 because you might have the denominator. If it goes down, that's all good. Yeah. So okay, that's it. Yeah, it's at least, right? So what he was saying, you may actually have used the set in the optimal set. And now maybe there's a set cover that covers the remaining items with only k minus 1 sets. So that's right. But that's only better, right? Because 1 over k minus 1 is better. Okay. Okay, so when do we stop? When the number of items is 0, less than 1, right? Then you're done. Okay? So when nt is less than 1, you mean there's no items left, right? Because they're integers. The items are integers. Okay? So this is it. For what t must, when is this thing, n0 is just n, the original number of items. At what t must this be true? Well, what do you think? Which one is it? There's some t by which it's true. Anybody? A, B, C. Okay, it's Friday. Okay, so everybody's like, it's almost 5. The Bears lair is open. What are you doing? Okay, so is the Bears lair even a thing anymore? I don't even know. So yeah, okay. So you get beer there, right? So okay, so you can plug in this. You plug in this and you see that C works, obviously, right? You can see that. It's absolutely clear to nobody in the room. Especially not me. So, okay, so in more detail. Of course you remember this. 1 minus x is less than e to the minus x. Because we love this. We love this. We love e, right? Oh, yeah. You don't remember it. Who remembers it? That's the figure. Clearly 1 minus x is the blue line. And the red line is e to the minus x. You can talk about Taylor. You can do any number of things. It's a lot of fun to figure this out. You can prove this in 10 different ways. That's my proof. So now what I'm saying here, this is 1 minus x. Now that's less than e to the minus x, right? Strictly less than, as long as x is not equal to 0. Okay? And then you get, I just take the t inside, and then now I plug in t equals k ln n, and then I get e to the minus ln n, which gives you 1 over n. Right? Voila. Okay? So at this time, after this many time steps, once t is this large, this expression, which is an upper bound on this number of items left, is less than 1. When this expression is less than 1, that means the number of items left is 0. So after this many iterations, you have 0 elements left, and you must have covered all the elements. Okay? Okay. So now this was the number of sets is at most k ln n. Okay, we assumed the optimal is k, right? That's what k is. This number. Where did it come from? It was actually our assumption that there was a solution of size k. That's how our algorithm worked. So now what we're saying is we're within ln k of optimal. So which is the best possible? Now, it's not the best possible. I'm telling you the optimal is k, but it's sort of the best possible for us to do because we're just not that smart. Okay, so we can't do better than ln n. I mean, well, it's not us. It's not even that we're not that smart. It's that we don't believe it's possible to compute this thing efficiently with a better factor. Okay? And what I'm saying is this, is we did not, here, unlike the other greedy things, we found the optimal solution. Okay? Now, the question is there a better analysis of the greedy algorithm? And it's no, and the answer is in the book. You can look at problem 533. It gives you an example where the greedy algorithm does poorly. Okay? So the idea is that two sets cover all the elements. And there's another set that covers slightly more than half of one half and slightly more than half of the other half. Okay? And then you recurse, and you're going to sort of get log n sets in your example. Right? Because you again have two elements that cover all of it, but you have you have another set that covers slightly more than half of what remains of each one, and then you go on. Okay? Is there a better algorithm? Okay, so here, this is not saying you can't do better, because there could be a different algorithm. This is just saying that greedy doesn't do better. And so we say probably not. And this is, again, one of these things where P and NP come up. And P is more later in this course, okay? So P is you when you're saying, well, I think that's a good joke. NP is me when I'm saying, I need to make up a good joke. Okay, so roughly that's what it means, right? One is harder than the other, right? I mean, especially for me, okay, to make up a good joke. All you have to do is check if it's true, right? That's what these things mean. The N means I'm making up something, okay? And I'm making up something that you can check and you can check, okay? But that's a really great description, but you don't believe me at this point, so that's fine. So now we're going to do the disjoint data structures. We're going to do path compression. Okay, so for this, I don't know. Okay, so we remember that, okay, here's the data structure. Okay, so we're doing a make set, find. We have this pointer structure, and everybody starts out with a pointer to somewhere. And the find, you assign your pointers. You just follow the pointers to the root of this pointer structure. And union is when you join two elements, you join the roots. Okay. So some things to notice about this is that, let's see. Okay, so in this structure, right, the parent always has a higher rank because of this. Okay, that's the things to remember. Now, once you're an internal node, once you're not a parent anymore, you never become a parent. Right? You never become a root. Because only roots point to each other. Okay? Okay, so now finally, let's see. Okay, so this one I need to be from Texas. Okay? So, because this is big. Okay? So, and so I got my Texas shirt on. So, let's Pepe's since 1969. Okay, so I would scramble up the little money and go buy a taco once in a while when I was a kid. So it was bad. The tacos were bad there. Okay. I mean, it's the white guy who takes it. Pepe, I don't know who Pepe is. So he didn't either. Anyway, so there's this rank. If you have two nodes of rank k, now this is subtle. You have to pay attention. Okay. So rank of x equals rank of y. Okay, these are two vertices. Think about their trees. Can they contain the same nodes? No. Never. At no point in time did they contain the same descendants. Okay? And in fact, how many does each one have? At least. Each has 2 to the k, right? That's what we proved last time. Because we're doing union by rank. Okay? So any two, say, internal nodes of rank k, they have the people who point to them are disjoint. The set of these things are disjoint. Okay? So now we're going to add something to this procedure to find. What we're going to do is, this was the old find, and then what we're going to do is we're going to point all of these guys to the root. The old find just went up that path, and the next time you do a find on x, it would do the whole thing again. This time, if you do a find on x the second time, you don't have to go through all these nodes again. So this is path compression. So every time you do a find on x, the next time you do find on x, it's going to be the same thing. Right? You're going to get the same answer. Right? You're going to get R. Or you're going to get whoever R points to. But you're going to have to go through R. So why not just skip and go to R? So that's what this says. It says I change my pointer to go to the root of the current tree. Okay? Is that clear? That's path compression. Do you see why it's called path compression? See, there's a path, and you see it's compressed? Yeah. Okay? This path for x used to be this long thing, and now it's compressed. Right? Okay. To 1. Okay. Okay, so is this better asymptotically? Is it always going to produce? Is every find going to be faster now? Not necessarily, right? You saw already the first find here may have taken a long time. The second time you do the find, it's faster. But the first time you did that find, it wasn't particularly fast. Okay, so we can do... so this is the path compression. Okay, so it doesn't get better asymptotically. Okay, the rank properties still hold. The rank to the parent is still higher and greater than 2 to the k in rank k. Right? Every find is asymptotically faster. So clearly we can't do worse than log n time. So do you see how to make it take O of log n time? You just do unions here, right? You union C and B, you union B and C. You do this in a big binary tree. And then you union these guys, you union C and this one, and you just do a big binary tree. So continue. And the union builds a tree. And and after a long set of unions, you do a find, this path will be O of log n. Right? You just build a binary tree up. And never do a find. Or always just do finds on the root. Okay? So this is a problem. We're not doing any better. Okay? So I did path compression, and now I'm saying we're not doing any better, at least for the worst case on a find. It could still take theta of log n, just like it did before. Okay? Okay, show that. But now what I'm going to say, well, the whole point of it was average. Right? The first time we did it, we paid. We paid for the whole path. The second time, it's very efficient. So the third time, it's efficient too. So we want to say, well, okay, maybe on average over all the finds, I don't spend too much time. Okay, that's the idea. Right, so even here, like once I do this find on A, I get a short, next time I do a find on A, I'm fast. Not only am I fast on A, I'm also fast on C and D and all the paths, all the go nodes there. So I'm really fast. I made it better for a lot of people. If I spent a lot of time, I made it better for a lot of people. Okay? Because everybody's path gets compressed. Okay, so now, okay. I think I need a taco. Okay, show that m finds takes O of m log star n in product. What the heck is log star? Okay, log star is a number. It's a number of times one takes log to get to 1. Okay, that's an odd statement. Okay, what's log star of 16? Okay, let's think about it. I take log base 2. Let's do log base 2. Log of 16. If I take log of 16 once, what do I get? What is 16? 2 to the 4. If I take log base 2 of 4, what do I get? 4. Yeah, 4. Nice. Okay. So and then what if I take log base 2 of 4, what do I get? 2. And then I take log base 2 of 2, what do I get? Yeah, so that was, what is this? What how many times did I take log? I forgot. 3. Okay, 3 times. Is that clear? So another way to see it is we're saying, how high is this stack of 2's to get to 16? Okay? We're just measuring the height of the stack of 2's. Right? Because you take log, you decrease the size by 1. So it's how many times do you need to decrease the stack of 2's to 1? Okay? This exponentiation, tower of 2's. Heights of powers of 2's. So what's log of a million versus log star of a million? Okay, I won't make you do it. So it's 20. This log of a million is the number of bits in a million, which is roughly 20. This is 5. You just take log a few times, you'll see, right? Well, now let's talk about a big number. A million's tiny, right? We can talk about a number, a million to a million. Like, that's even faster than these quantum computers can do. It's like, wow, okay, that's huge. You never even care about a number that big. So this one, what's log star of this? Well, log star of this brings it down a lot, right? It already takes the exponent out. Okay? So this is 20 million versus 6. So log is a pretty slow-growing function. The log star is really slow. 6, right? Yeah. Slow. Grows very slowly. Okay. So show that m takes m of log star. So now these things are super efficient on average, is what it's saying. Okay? Shockingly efficient. Okay? So we're going to do this by, we already saw we can't bound the worst case time for a find. One of the finds may take like infinitely longer because log n is horribly big compared to log star n. Okay? So who else amortizes? What does an amortizer? Bankers amortize, I guess. I don't know whether that's true, but I think they do. And they hand out money. Okay, so how do you amortize? So what it is we're going to talk about money here. So we're going to sort of say, we're going to hand out some money and use it to pay for each pointer change. Each time we find a find, remember in path compression, we do a find, and this guy needs to change his pointer. So what we would have done is, I don't want to change my pointer. We're going to give him some money to change his pointer. He's like, if he has some money, he'll say, okay, I'll take one of the dollars you put in my account, and I'll change my pointer. Okay, so that's how we'll keep track of how many pointer changes there are over the whole algorithm. Right? What we want to see is how many pointer changes there are in all the finds. Okay? So what we're going to do is we're going to only hand out m log star n dollars, and it's going to budget balance. We're not going to have more pointer changes than dollars. Okay? So that's the idea. Okay. So what we're going to do is we're going to hand money to internal nodes, not to the root, because the root doesn't change pointers, right? Once you're at the root, you don't have to do any work. You're not doing find as long as you're at the root. Okay, you're not changing your pointer. Your pointer goes to yourself, you're happy. Okay, when a node becomes an internal node, the rank will no longer change, right? You only change the ranks of the root nodes, right? You change the rank when you merge two sets, and you change the rank of one of the root nodes. So you never change an internal node. Okay? Okay, so now you divide these non-zero ranks into levels. Who cares about the zero ranks? We'll not worry about them right now. Okay? Okay, so because the zero ranks don't point, whatever. They're just zero. Okay, so now we're going to divide them into levels. So the first, into groups, right? This is groups, okay? So one of them will have 1. The next one will have 2 through 4. The next one will have 5 through 16. So the key here is, what is 16? 16 is the last number in the previous group exponentiated. Okay? 16 is 2 to the 4. The next group's endpoint would be 2 to the 16. Okay? So every group, the endpoint of the next group is exponentially, you take the exponent. Okay? So I should have written the group right before here. The last element in the previous group here, right before the k plus 1 there, is k. So the last element in this one is 2 to the k. What's the last element in the next one? 2 to the k. Okay, so we're building this tower of 2's. Okay? How many groups of ranks? Okay, the maximum ranks can't be larger than n. In fact, it's not even larger than log n. We already proved that. So the maximum rank in here is not bigger than n, for sure. Okay? So, and every time we're raising the power of, so now if you take, let's look at the maximum group. We take the log of that guy, it's going to be in the previous group. And you take the log of that guy, it's going to be in the previous group. So the maximum group can only be log star away. There can only be log star n of these groups. Because every time we're making these groups hugely bigger, we're raising the last group to an exponent. Okay? Each group grows by powering of 2. So how many internal nodes ever get rank R? If you just pick one rank, I'm not talking about a group here, but if you just think of one rank, how many internal nodes ever have rank R? Well, any rank R node or pointer has to have 2 to the R nodes in it. Any 2 rank R guys have to have separate sets, right? That's what I said on the very first slide. So this says there's at most this many, right? Is at most n over 2 to the R. Okay? Of any rank. So each contains 2 to the R when it's root, and they're separate nodes. Okay? Okay. So now now we've set up this thing, we're going to set up a scheme to pay people. We're going to hand out money to internal nodes since they change pointers and find. We talked about that. When a node becomes an internal node, the rank won't change anymore. So whatever money we gave them, that's the money he should have, because we gave them the rank. We gave them something that corresponds to their rank when it became as high as it could be. Okay? Okay. So what we're going to do is, if you're in this set of ranks, any one of these ranks, you get 2 to the k dollars. Okay? You get $1 million, you get $1 million, you get 2 to the k dollars. Okay? So there's only n over 2 to the r internal ranks of rank R. So how many dollars do we hand out to everybody in this group? That's what I'm going to try to figure out. So how many dollars do we hand out to all the nodes who have ranks in this group? Okay. So in a group, there's somebody in the group. There's somebody of rank. There might be people of rank k plus 1, but there's only 2 to the k. There's only n over 2 to the k plus 1 of them. Right? There might be some of them who have rank k plus 2. There's only n over 2 to the k plus 2 of those. And so on. So we add up these things for each rank. We know an upper bound on how many vertices have that rank. We add them up. We multiply by the 2 to the k we get. This is a geometric sum. Right? Each one of these terms is smaller by a factor of 2. So it's twice the first one. Okay? And so then you get this is n, or definitely order n. Okay, now we said before there's log star n groups, so that's the total amount of money you handed out is m log star n. Okay. Okay, so now we're going to bound the cost of the find operation. And I lied a little bit. Some of the parts of the find operation we're going to go ahead and just charge. We're just going to pay the cost. some other parts of the find operation, we're going to use the dollars. But for each find operation, the amount we're going to pay is at most log star. Where you just say, you just have to change. I don't care. You have to change. I'm not going to pay you $1. Okay? That's log star of them. And then there's all these others that people get paid for. Okay? Okay, so remember, this is path compression. So now we have two cases. And the two cases of whether we pay somebody or not are based on this. So if rank X, right, what happened here is X pointed to Z. And after path compression, now X points to R. Okay? Now, if rank X and rank R are in different groups, we tell X, okay, you're different groups. We're not gonna pay you. But that guy's a god. He's in the next group. Okay, so it's good for you. So that's fine. Okay. The other guy, if Z and R are in the same group, we're going to say, hey, here's this $1 that we allocated to you. Okay, so there's two kinds of pointer changes in a find. Either you start pointing to somebody in a different group, or you point to somebody in the same group. Okay? Same group of ranks. Okay, they're definitely higher, but they're the same group. So there's some O of 1 because you have to do something when you call find. And then the cost of changing pointers to point to higher ranked nodes, right? That's all there is, right? The 0 ones may change their pointer, but we don't care about the 0 ones. There's only one of them in the find. Okay. So now the per operation part, it's log star and pointers point to a node in higher group, right? This whole path here goes up in rank. So only at log star n places can you jump up a group. Okay? Okay, so that's one. And now the total per operation over m finds is m log star n, because for each find we're going to pay for this. We're going to pay for the change of pointer where you pointed to somebody in the higher group. Okay? Now there's the amortized part. We're going to talk about Z. So that pays for all the pointer changers that look like rank of X and rank of R in different groups. Okay, node uses its dollars to pay for changing a pointer within a group. Okay? So remember, this is what a group looks like. So now both Z and R are in this group. Okay? So it used to be Z pointed to somebody in this group, and now it points to somebody higher in this group, because the ranks only go up along the path. So how many times can Z change his pointer and stay in the same group? Right? The number of ranks in here is at most 2 to the k plus 1. Right? So the number of times he can change his pointer over the whole algorithm, right? Once you change your pointer to a higher rank, you can only change it to a yet higher rank. You can never change your pointer to a lower rank. Okay? Because the ranks along these paths go up, and you're always going to an ancestor. Okay? So the number of times you can change your pointer and stay within the group is only 2 to the k. Well, okay, I'm off by 1, but okay. Okay, now each group, each node in the group has 2 to the k dollars, right? That's how many dollars we gave each node in this group. Okay? So that's enough money. So everybody, all the people in this group had, 2 to the k dollars, and you can only change the group inside the group 2 to the k plus 1. So let's say we're off by a factor of 2. We're better than JP Morgan and that, so that's fine during the crash anyway. So the total money was n log star. Okay? Okay, so this is the averaging argument. So you see why I have to wear this shirt. It's pretty tough, but it's kind of beautiful, right? Okay. So that's the total find cost, is O of m n log star. We have this part. We just say, if I change my pointer to somebody in a different group, that only happens log star n time. Inside of the group, I only change 2 to the k times. And that's what I got. That's how many dollars I got. And I know I only handed out n log star n dollars. Okay? Okay. Oh my God, it's 5. So lecture, Wow. Okay. So it even went over the line. Okay. Okay, so there's some, I should let you go, but it's fancy business. Can we do better? There's ways to do better. But I don't understand them. Okay. and this is lecture in a minute. So happy Friday.